Hi students, welcome back. Today we are going to look at another problem on LeetCode called the code schedule. So let's look at the problem statement first. So the problem statement says we are given num n number of courses that we have to complete. So the courses start from 0 and they go up till number of courses minus 1. Okay. And we are given an array prerequisite which contains another array which has two numbers in it, which is AI and BI. So this basically indicates that you have to take, if you have to complete AI, you must take course BI first. That means to complete AI, you have to complete BI, which basically means AI is dependent on BI. Okay. For example, the pair 01 indicates that you have to take course 0. You, in order to take course 0, you have to take course 1 first. So this means in order to complete course 0, you have to finish 1 first. Finish 1 and then you can take 0. So the objective is return true if you can finish all the courses, otherwise false. Okay. So if you clearly see here, the courses form nodes in a graph and the dependency is basically edges in a graph. So this clearly is a graph problem. Okay. This is the hint for us to, think of it like a graph problem. This in a way is a different representation of an adjacency list. Okay. So now that let's look at few examples. Okay. Um, the example one states the input is number of courses equal to 2 and the prerequisites are 1 to 0. Okay. Here in this case, actually, there are two courses and one is dependent on 0. So you will take course 0 first and then course 1 and it is pretty clear. Now in the second example, the prerequisite says, again here also two courses, but the prerequisite says you have to take uh, course 0 for for course 1 and course 1 for course 0, which is not possible, which is why here you have to return false. So if you look at the graphical representation of it, you are saying for course 1, okay, you have to take course 0 and for course 0, you have to take course 1. So in a way, what we are saying is it is forming a loop or a cycle. So essentially, this boils down to the problem of detecting a cycle in a graph. So with the help of the prerequisites, we have to form an adjacency list or a graph, and we have to detect the cycles in a graph. And the other thing to note is this is a directed graph, not an undirected graph. Okay. So if there is a cycle, that means one course is dependent on itself or something in the chain, you won't be able to complete the schedule, which is when you have to return false. If there is no cycle, then you can form some kind of a schedule, and in that case, you'll have to return true. Okay, so let's look at it through another example. Let's say this is our graph structure. Okay, let's say, let me reduce the font size. Okay, let's say we have one node 0. Okay, and And let's say there is another node like this. So which basically we are saying course 0, to take course 0, you have to take course 1 first, and for course 1, you have to take course 3. Similarly, for course 2 also, you have to complete course 3. For course 0, you are dependent on 1 and 2. Whereas for 4, it is independent. You can take it in any way. So here, if you see, this is a directed graph and it is not connected. Okay. So which is why you'll have to traverse all the edges, not all the nodes, not just one of the nodes. So the connected nature of it is also important. Now, how do we detect the cycle in this graph? What we were saying was if there is a cycle, it's not possible. So in a graph traversal, the two things that comes to our mind are DFS and DFS. So for DFS, what we do is we traverse level by level, which means let's ignore 4 for a moment, which means we'll go like this. Okay. Whereas for DFS, what we do is we go in the depth. Okay. Now, how do we define a cycle? So, a cycle is formed when in a path. Okay. So, here the path is, let's say, there is 0, 2, and 3. Okay. In this path, if there is any back edge pointing to some node in the same path, it can be 3 to 2, it can be 3 to 0, 2 to 0, anything. If there is any such back edge, then we say that there is a cycle. Okay. So in case of BFS, since we are doing level order traversal, forming this path is not possible. Okay. Whereas DFS goes to the depth, that is, it traverses the one path completely. So detecting that back edge is easy in DFS, which is why for this use case, DFS is best suited. Okay. So now coming to the actual algorithm, what will we use? So the algorithm which I am going to discuss is discussed in this book, Introduction to Algorithms, the very famous book by CLRS. I think it's in section 22.4 or so. Okay. So the algorithm says, let's take three sets. Okay. Let's call them white, okay, gray, and black. So all your nodes will be in one of these sets. White is nothing but unvisited. Okay. Bright gray is nothing but the current path. Okay. So when you're traversing from 0 to 3, 0 to 3 is your path. And black is nothing but the usual visited set which we keep. Okay. So as a first step, what we will do is we'll keep all the nodes in the unvisited or the whitelist. So 0, 1, 2, 3 and 4. Initially, all of them will be unvisited. So we'll start with DFS of one of the nodes in the unvisited list, which would be DFS of 0 to start with. Okay. So when we are starting a DFS, that means we are forming a new path. So the 0 will move from white list to gray list or the current path list. So DFS 0 has two children. So for simplicity's sake, let's construct the adjacency list here. So 0 has two children. 1 has 3. 2 has 3. Okay. 3 has no children. 4 has no children. This is our adjacency list. So DFS of 0 goes to DFS of either 1 or 2. So let's start with 1 for now. So as soon as we traverse 1, what we do is we move 1 to the gray list. Okay. Now 1 has moved to the gray list, and then we go to children of 1, which is what is the child of 1? 3. So we go to DFS of 3. So similarly, 3 will also move to gray list. Okay. So 0, 1 and 3. 0, 1 and 3 are in the current path so far. But for 3, there are no children. Okay. Which means the traversal of 3 node is complete. So now we will start going back to the stack. So when the traversal of node is complete, then we will mark the node as visited, which means we will move the node from gray to black. Okay. So now we move 3 to black. And we go back to its caller, which is 1. Does 1 have any other children? No. So that means all the 1 is also visited. So we move 1 also to blacklist. Now we go back to 0. Does 0 have any other children? Yes, 0 has 2. So we will do DFS of 2, and we will move 2 from white to current path. Okay. Now we have to look at children of 2. Children of 2 is 3, but 3 is already in the visited list. So we don't have to do anything. That means there are no unseen children of 2, which means 2 is also process. We go back to 2. Now, this moves to its caller, which is DFS of 0. 0, all the children are now traversed, so 0 is also visited. We move 0 to blacklist. Okay. So this completes the one of the connected components traversal, and so far we didn't find any cycle. Okay. But if you see the unvisited list, there is one more node. So let's start DFS traversal for that. Okay. Now we start with DFS of 4. So 4 moves from white to gray list. Does 4 have any children? No. So 4 directly moves to blacklist. 4 is visited. Okay. So in this case, we didn't find any cycle at all. Okay. So let's look at another example which has a cycle. Then this algorithm would be more clear to you. Okay. So let's take one node 0. Okay. 1. Okay. 2. Okay. 3. And let's say this points back here. Okay. So this is a cycle. So what we are saying, what is the adjacency list here? 0 has two neighbors, 1 and 2. 1 has no neighbors. Okay. And 2 has 3. 3 has 1. Okay. Now let's do the same graph traversal. We have white or unvisited and gray or current path and a black set. Okay. White is unvisited. Okay. This is current path and this is visited. Okay. When we start, we put all the nodes in the unvisited set 0, 1, 2, and 3. So we start with one of the nodes in the unvisited list. So let's start with 0. So let's start with DFS of 0. Okay. So when we start, what we do? We move from unvisited to current path, which is gray list. Okay. So DFS 0 has two children, 1 and 2. Okay. Let's go to 1 first. Let's do DFS of 1. Okay. So 1 moves from white to gray list. Does 1 have any children? No, which means traversal of node 1 is complete. So it moves from 1 to blacklist. Okay. And this stack goes back to its parent. Now let's go to DFS of 0. What are the other children it has? Other unvisited children. 1 is already visited. So we will do DFS of 2. Okay. We are doing DFS of 2, which means 2 will move from white to gray list. Okay. Now, what is the children of 2? 2 has 3 as children, which is unvisited. Okay. So we will do DFS of 3. Okay. 3 will move from uh, here to here. Sorry, here 1 we have to move, right? So this is 1. Okay. DFS of 3. Now, what is the children of 1? Children of 3. Children of 3 is 0. And 0 is in the current path because it is in the gray list. So, children of 3, child of 3 is equal to 1 and 1 is already in the current path. Okay, which means it is a cycle. Okay, so the definition of cycle is if we find a child which is already in the current path, which means a back node exists, right? So here if you see what we did, we went from 0 to 2 to 3. Okay, this is our current path. Then we found that 3 has a node from 3 has a child to one of the nodes in the path, which clearly shows it's a back edge. So in this case, we call it a cycle. Okay. So that is how we detect a cycle. Now let's write code for this. So in the code, what we will do is instead of representing this white, gray, and black as three separate sets because it will become operationally difficult. What we will do is we will uh, take labels for them. Let's say in the visited set, we will call whites as -1, grays as 0, and black as 1. Okay. When we write the code, it will be clear for you. Okay, so let's define those labels first for the white, gray, and okay. So let's call three integers. I'm just defining these labels for readability. That's all. Okay. So our visited set would be an array. Okay. So let's define the visited array. So each node, uh, let's say 0 is in the white list, its value would be -1. 0 is in the gray list, its value would be 0, and so on. So we are just taking one array and representing different sets through different values. That's all we are doing. We're just optimizing it. That's all. Okay. Let's also define a adjacency list. Adjacency list is nothing but list of lists. Okay. So now we have to initialize both of these things. Okay. For int I equal to 0, I less than number of courses. First, let's create an empty adjacency list for each of the node and initialize all of them to white. So what we are essentially doing is we are putting all the nodes in white first and creating an empty adjacency list. Okay. After this, what we will do is we will update all the neighbors of the adjacency list. So how will we get the neighbors? Neighbors we get from the prerequisites. Okay. So for each prerequisite, we will update the adjacency list. So prerequisite is going from A to B, right? And we are saying A is a parent of B, which is what? Which is why we are saying at uh, A, add P. So here in the problem definition, we are clearly told that these are all unique pairs. So we don't have to worry about duplicity or anything here, which we can simply just add it. Okay. Now, till this point, what we have done is we have created a visited array. We moved all our nodes to unvisited and we created an adjacency list representing our graph. Okay. Now, what we have to do is we have to pick one node from the unvisited or the white set and run the hash cycle algorithm. Okay. So, what do we do? We traverse all the nodes, and if any of them is visited, unvisited, which means any of them is in the white set, okay, we check if it has a cycle. Okay. If it has a cycle, that means if it has a cycle, that means we cannot complete this course structure, which is when we have to return false. If it doesn't have a cycle after traversing all the nodes, then we can return true. So here, instead of just randomly picking one node, we have to traverse all the nodes because our graph is not connected. Okay, there can be disjoint connected components. So we won't be traversing every, I mean, we are not doing DFS on every node, but we are doing DFS on every connected component. That is ensured by this check. We are doing if visited equal to white. So after the first traversal, all the nodes in that path will become black. So which is why we won't touch those nodes. Okay. Now let's write the actual function, which is the hash cycle. Okay. So our hash cycle returns a boolean. It takes a vertex v. It passes visited set and adjacency list. Okay. So as soon as we come here, what we have to do? The first thing we have to do is we have to move this node to the gray set, which is nothing but just updating the visited to gray. Okay. And next step is for each of its child. So get all the children. You get the children from the adjacency list. So for each of its child, we check if the child is in the current path. How do we check if the child is in the current path? By checking if visited of child is gray. So this means child is in the current path. Then this shows it has a cycle. If the child is in the current path, it has a cycle and we immediately return true. Okay. Now what is the other case? The child may not be visited so far. Okay. If the child is not visited so far, which means the child is in the white list, what we do is we have to run DFS on its child, correct? So we just run DFS on its child, and if that returns true, we can just return true. We don't have to further process. That subtree has a cycle, which means the whole tree also will have a cycle. So if the child is white and it has a cycle, then we just return true. Now, what do we do in case of black? Blacks are already visited. We don't have to visit them or do anything. So we don't have to write any case for that. Okay. So we mark the current node to the current path by making it gray. And for each child, we are checking if the child is in the current path. If it's in the current path, it has a cycle. If the child is in the unvisited list, we run DFS on that list. If the child is already visited, we don't have to do anything. If the child is in the unvisited list and it has a cycle, then the parent also has a cycle. We just return true. Okay. Now, if what happens if none of this is true? I mean, we processed all the childs properly. There are no cycles and all. That means the current node visiting is complete. Okay. So we move it to blacklist. Okay. So initially we started with moving it to gray list. We processed all its children and found that there are no cycles. Then we move it to blacklist and we return false. At this point, there is no cycle. Okay. Let's run this and see. Okay. Let's submit this. Okay. Yeah. It ran in 3 milliseconds. So what is the time complexity of this solution? We are touching all the nodes only once. Okay. Which is why the time complexity would be order of V plus V, which is vertex and edges. Basically, same as um, what is it? DFS. Okay, in the space complexity, we are using an additional visited array, and also the stack will contribute to it. So it would be order of V. Okay, yeah, that's all for this video. This is a bit complex problem on graphs. So do try it on your own and do a dry run with an example. That will help you understand it better. And clearly understanding the distinction between BFS and DFS and why you can't use BFS here is really important. Okay. As a homework, you can take cycle detection in an undirected graph. Okay. You can try with BFS in that and that will work. So if you do a dry run, you will know why and you will understand the difference of it properly. Okay. As always, please like, share, and subscribe. Thank you for watching. Happy coding.